Hi everyone, I am Mr. S. Vanchinathan, Assistant Professor, Department of Physics, K.S.Rangasamy College of Technology, Tiruchengodu. Today, we will discuss Module 3 of Engineering Physics, which deals with magnetic materials and dielectric materials. Magnetic and dielectric properties play a vital role in modern technologies such as memory devices, transformers, sensors, capacitors, and many electronic systems. Today, our outline of magnetic materials in this model, the origin of magnetic moment in the materials, and then classification of magnetic materials into dia, para, and ferromagnetic material, and the domain theory of ferromagnetism, the process of magnetization through domain wall motion and domain rotation. Finally, the different types of energies involved in domain growth. Each of these concepts builds up a complete understanding of magnetic material is behave as differently when exposed to magnetic fields. What is magnetic material? A magnetic material is any material that can be easily magnetized when an external magnetic field is applied. These materials either have permanent magnetic moment or develop an induced magnetic moment under an applied field. For example, iron and cobalt are strongly magnetic because of their internal structure. And then origin of magnetic moment. The origin of magnetism lies in behavior of electrons inside atoms. Electrons contribute to magnetism in two ways. The first one, orbital magnetic moment, and then second one, spin magnetic moment. Orbital magnetic moment is nothing but due to motion of an electron around the nucleus. Spin magnetic moment is nothing but due to the intrinsic spin of electrons. And then Bohr magneton, the total magnetic moment of an atom in the vector sum of these two contributions. A fundamental unit of magnetic moment is called Bohr magneton. Bohr magneton, one Bohr magneton is E h cross divided by 2m. The value is 9.27 into 10 power minus 24 ampere meter square. If the electrons are paired, their opposite spins cancel each other, the magnetic effect, but unpaired electrons exist. A net magnetic moment arises. Applications of magnetic material. Magnetic materials have wide application in engineering and technology. Soft magnetic materials such as silicon steel are used in transformer cores and electrical machines to reduce energy loss. Permanent magnets are used in loudspeakers, electric motors, and sensors. Magnetic storage devices such as hard disks and tapes use ferromagnetic materials. Ferrites are used in high frequency applications like microwave devices and antennas. Thus, the study of magnetic material is not only theoretical but also highly practical. Basic definitions of magnetic material. Dipole moment. The magnetic dipole moment is the product of poles strength and distance between two poles. And then magnetic dipole, the two equal and opposite magnetic poles separated by a distance. Magnetic intensity is nothing but magnetic flux density, the measures of internal magnetic field. And then magnetic field intensity, the strength of applied external magnetic field. Magnetic permeability, the ratio of magnetic induction and magnetic field intensity is called magnetic permeability. And then magnetic susceptibility is nothing but the ratio of magnetization to applied field intensity indicates how strongly magnetic materials are magnetized. These definitions from the foundation of classify magnetic materials. And then classifications of magnetic materials. So the magnetic materials is classified into three categories. The first one is diamagnetic material, and then paramagnetic material and ferromagnetic material. These magnetic materials, the classification, in materials without permanent magnetic moment, the materials with permanent magnetic moment. The materials without permanent magnetic moment is example is diamagnetic material. The material with permanent magnetic moment is example paramagnetic material, ferromagnetic material, and antiferromagnetic material. And ferrites is the classifications of magnetic material. So the diamagnetic materials or electrons are paired, so magnetic moment cancel. So magnetic moment is zero for diamagnetic material. These weakly repelled the magnetic fields. The example is copper, bismuth, etc. Paramagnetic materials, unequal number of electron spins with opposite spins, the net magnetization is small but positive. So the example of paramagnetic material, so aluminium, platinum. And then final one is ferromagnetic material. So the large number of unequal paired electrons resulting in strong net magnetization. So therefore the ferromagnetic material example is iron, cobalt, nickel. The susceptibility value is negative for diamagnetic material, positive for paramagnetic material, and more positive for ferromagnetic material. And then domain theory. So domain theory to explain the ferromagnetism, according to this theory, a ferromagnetic materials is divided into small region is called domain. When magnetic field is applied, these magnetizations rearrange and producing a strong magnetization. This theory explains why ferromagnetic material can be become permanent magnets. And then process of magnetization, the process is magnetization occurs in domain wall motion and domain rotation. When a small field is applied, the domains aligned, field growth and domain wall motion is occurs. And then domain rotation, when the field is again further increases, the domain rotates. Thus a result, the entire materials become strongly magnetized. And then types of energies involved in the domain growth. Several types of energies factors involved in domain growth. The first one is exchange energy, and then second one is crystalline energy, and then domain wall energy and magnetostrictive energy. So conclude our model 3. The classification of magnetic materials, also explain the domain theory and process of magnetization supported by the role of different energies in domain growth. Understanding these concepts in essential in the design of electrical machines, storage devices, and advanced electronic systems. So thank you for all.